The concept of infinity is directly connected to anything that would have a 0 in the denominator, which is going to ultimately produce asymptotes. And so we'll be talking about how infinity is connected to the idea of a 0 and how it's connected to the production of an asymptote. So let's kind of go through some math logic. If you divide something by a number that's larger than it, what happens to your result? So if I take 10 and I divide it by a number that's larger, like 90, what happens to the number I started with? It gets smaller. All right, so if you take a number and divide it by something larger, it produces a smaller result. The converse is true. When you divide by a smaller number, and then what would happen? Would you get a larger, and you get a larger result. So like if I take the number 10, something smaller than 1. I was talking about small, like small numbers. Okay. If you take a number 10 and divide it by half, then you get 20. So it just made your number bigger. Okay, we're talking about numbers that are small enough, smaller than 1. So then the question is, well, what happens when you divide by 0? And you've heard me talk about this for about a week now. Okay, what happens when you divide by 0? And a lot of you are saying, like, I get undefined, and okay, so we need to kind of reframe how we think about dividing by 0. So before this, you've been saying we get undefined. Okay, but I'm going to say it really? Yes. If you divide by plain old 0, you're allowed to call that undefined. But we're going to get around this system, and we're not going to actually divide by plain old 0. We're going to divide by the two sides of 0. We're going to divide by 0 plus, and we're going to divide by 0 minus. So we're just going to, this is like, I'm not touching 0, I'm not doing it, okay? I'm just right on either side of it. So when you divide by 0 plus, you get positive infinity. And when you divide by 0 minus anything, you're going to get negative infinity. Unless the k is negative on the top two, then I guess you're going to get positive infinity because the two negatives would make a positive. But we'll just stick with this. You're going to get a positive or negative infinity when you divide by 0 plus. So you're going to have to stop telling me that it's undefined and start telling me what kind of infinity you get, because you're going to get one or the other. So in this case, I cannot plug in 1, because if I plug in 1 directly, I would get -3 with 1 plugged in, and I would get 1 minus 1, which is going to get -3 over 0, which is undefined, which is not what I want. So instead, I will be evaluating the two sides of 1. I'm going to evaluate 1 from the left, and I'll be plugging that into -3x over x minus 1, and I will compare that to 1 from the right, and I'll be plugging that into -3x over x minus 1. So check the two sides of 1. If something that you plugged in makes undefined, then check its two sides. So that's going to give me -3 times 1 minus over 1 minus minus 1. My numerator will give me -3 minus. My denominator is going to give me 0 minus, which is going to produce a type of infinity. The numerator is a negative number. The denominator is also a negative number. Both of them are negative. This is a negative divided by a negative, so that produces positive infinity. When I plug in the other side of 1, I'm going to have -3 times 1 plus, and then 1 plus minus 1. That will give me -3 plus over 0 plus. The numerator is still negative. Even though there's a plus sign on it, it's still a negative number. but the denominator is now a positive number. So since I have one of each, I'll be producing negative infinity. So again, instead of telling me undefined, you need to check what side of infinity you're on. Yeah?
Why is it negative?
Why is which one negative on the bottom?
Oh, okay, never mind. You did say
Okay. Oh, whoops, I gave you an extra slide to do that work. Never mind, we already did it. Okay, skip that one. So numerically, when we work it out, we're going to get plus or minus infinity. On a graph, that means you're getting a vertical asymptote. And what the negative and the positive infinity are going to tell you is what you're going to be doing when you get close to the asymptote. As you get close to that boundary line of an asymptote, is your graph going to bend in such a direction that's going to shoot up? Or is your graph going to bend in a direction that's going to shoot down? That's what the positive and negative infinity are telling you about. So let's take a look at that. If you've got an asymptote, I'm going to do my asymptote in yellow. Okay, so if you've got an asymptote coming down here, your limit will tell you which direction your graph is going to head. So will your graph, as you come along here, and it encounters that asymptote, is it going to shoot down, or will it go to negative infinity, so it's just going to take off and head down, or will it go the other direction? And then what's going on the other side? So maybe a graph would be both of them heading down like that. That was called an inverse square, the graph that we learned in chapter 0. Or if they're going in opposite directions, that'll be a hyperbola graph that we also learned in chapter 0. So where will this encounter an asymptote? At 2, okay? It's going to encounter an asymptote at 2 because of the denominator. So we'll go ahead and we'll put our asymptote through here at the number 2, probably first things first. And then we want to figure out which direction are the branches of the graph going. So we would want to check, well then what is the limit as I approach 2 from the left of x over x minus 2, and what would be compared to the limit as I approach 2 from the right of x over x minus 2. So we'll check that out. I'll get 2 minus over 2 minus minus 2. So the numerator is going to be 2 minus, and the denominator will be 0 minus. So we want to think, my numerator is what kind of number? Positive. My denominator is what kind of number? Negative. So a positive over a negative is going to produce negative infinity. So that means as I approach this from the left-hand side, I will be approaching negative infinity. I am not going to grade the accuracy of the rest of your curve and your branch. I'm just checking, do you know where you're going in the general direction? Yeah.
Is 0 automatically determined as negative, or why is that?
Yeah, 0 minus is on the negative side of 0. If you think of a number line and 0 being neutral, 0 minus is going to be on the negative side of the number line. Yeah, whereas 0 plus would be on the positive side of them. All right, and so here if we're going to plug in 2 plus, we have 2 plus in the top over 2 plus minus 2. So that'll be 2 plus over 0 plus. Both of those are positive. And so my other side is going to be approaching that direction. That's what I'm checking for now, okay? Luke, you had a question?
I was just going to say that if there's an asymptote at y equals 0, but then you said like graph, like accuracy.
There's actually a horizontal asymptote at y equals 1, but that's another lesson for another day. Okay, that'll be Friday. We'll talk about horizontal asymptotes, and then we'll get those on there.
But we don't, we're not doing that.
Not right now. Nope, just vertical. Just vertical. All right. Where are the vertical asymptotes here? 2, yeah. and negative 2. Oh, there's two of them here. There's a vertical asymptote here, and there's a vertical asymptote going down here. So I've got two sides of two asymptotes. So I have 2, x equals 2 is one of them, and x equals negative 2. All right, if you go to the next slide, I've drawn the picture for you. So from the picture, let's put down what the limit values are. Okay, so Allie, this is the one, let's do negative 2 from the left. According to the picture, what is the limit value as I approach negative 2 from the left?
Negative.
Good job. All right, so negative infinity for that one. Okay, very good. All right, Henry Bleckner, what about negative 2 from the right?
Positive.
Good job. Okay, so that's this end of the branch. So we've covered these two ends of the branch. Okay, good. All right, Casey, how about positive 2 from the left? Yep, if you find the asymptote at positive 2 and then you find the arrow on the left side, it's definitely pointing up. So we have positive infinity. Okay. And then Jefferson, how about 2 plus, the limit approaching 2 plus? Okay, that's the negative infinity, so that's this one. So if you get your calculator, then you can just tell me what they are off your calculator. You don't have to show the work. All right, what about tangent? Where are its asymptotes? It's the actual question I'm asking. Where are tangents asymptotes? All right, Weston? Okay, plus or minus pi over 2. So I can put them wherever I want as long as I label them as plus or minus pi over 2 are the first ones. There's lots of other ones. Okay, but plus or minus pi over 2. And then I've got my graph I know comes through the origin and looks like this. And then there will be another asymptote on the right, and there will be another asymptote on the left. What happens consistently on the left side of every asymptote? Okay, on the left side of every asymptote, where am I going? Where am I heading? Positive infinity. On the right side of every asymptote, where am I heading? Negative infinity. So this is the left side of every asymptote. Okay, the left side of every asymptote is pointing to positive infinity. So I can generalize that this way. The limit as x approaches, okay, how often do these asymptotes happen? I know they're at pi halves and I know they're at negative pi halves, but how often does that happen? With a space of pi, right? So it's pi halves plus or minus k pi. The first one's at pi halves, and then every single one after that is pi away. And if I'm approaching from the left of tan x, that will always be positive infinity. And for all the asymptotes, pi halves plus or minus k pi from the right of tangent of x, that will always be negative infinity. Those are always the ones on the right side of the asymptote that will be pointing down. So you can generalize it. How, what's a pattern you see about asymptotes? Okay, we're going to press pause a minute. Yeah, Henry.
Do you need to define what k is for this one? Or is it-
K is always by definition an integer value, and I'm using all k's. I'm not skipping the evens or the odds. I'm using all of them. So K by definition is all the integers. Okay, we're gonna press pause for a minute. Find page 780 on your book, and I'm gonna give you a few minutes to get started on the first part of the homework assignment, which I'll put on the screen. What we need to talk about next is what if you get infinity in the denominator? So we've talked about what happens if you get 0 plus or 0 minus in the denominator. What happens if you have infinity in the denominator, either positive or negative infinity? And what kind of an asymptote does that produce? That's what we're going to be talking about next. All right, so watching out for where infinity happens. If you have a limit and infinity is the result, that's what we were just doing. If you have a limit and infinity is the result of that, that is a vertical asymptote. If you have a limit and the plus or minus infinity is part of what you are approaching, and you get a constant value as a result, if the infinity shows up somewhere else, that is a horizontal asymptote. So infinity is the key. Where does infinity show up in the limit? It leads to what kind of asymptote that you're talking about. Okay, so this is the definition of a horizontal asymptote. A horizontal asymptote will occur if you investigate the limit approaching positive infinity and that yields a constant. So B has to be a constant for both of them. If you get a constant when you've used infinity and you've plugged infinity in and that produces a constant. So it's different. If you plug in a constant and it produces infinity, that's a vertical asymptote. If you plug in infinity and it produces a constant, that is a horizontal asymptote. That is the definition. So we'll talk here about horizontal asymptotes. Just looking at the graph, I see that there are two kinds of asymptotes. There is an asymptote coming down the y-axis, but there also appears to be an asymptote coming across horizontally to split this into its two branches. So the limit, as I approach infinity from the right-hand side, I will always be approaching the constant value 1 from the positive side. I'm going to be above 1 and never touching 1. I will always be above 1, but I'll be very close to it. The negative side of the graph is the one that's heading out to the left. I will also be approaching the horizontal asymptote of 1, but I'll be approaching it from underneath. I will be a little bit less than 1 all the time. I will never actually get to 1. So because infinity right here produced a constant and a negative infinity here also produced a constant, that is the textbook definition of a horizontal asymptote. So the horizontal asymptote is the constant of 1. Okay, that's a coming through. How do we prove a horizontal asymptote? Not just I looked at it and it looks like it's 1 to me. How would you come about proving the horizontal asymptote? So if we have x approaching infinity, we are moving to the right. And that goes through quadrants 1 and 4. Okay, if x is approaching infinity, we're heading this way on our graph, and that's quadrants 1 and 4. If we have x approaching negative infinity, we will be heading to the left. That covers quadrants 2 and 3. If we're talking about y approaching infinity, now we're moving up and down. So we're moving increasingly up vertically. That will go through quadrants 1 and 2. So we'll be heading this direction through quadrants 1 and 2. And then if we have y approaching negative infinity, we'll be going down and we'll be going through quadrants 3 and 4. Just want to make sure everybody is clear on the quadrants and the directions. All right. Okay, what are you allowed to do with infinity and what are you not allowed to do with infinity? If you start with infinity and you add a constant to it, what do you get? What's infinity plus 3? What's infinity minus 3? Okay, so if you start with infinity and you add or subtract something to it, you're still with infinity. That is legal. If you take infinity and you subtract, or if you add infinity to already infinity, what do you get? Still infinity. Okay, no, there's no double infinity. It's just infinity. If you take infinity and you subtract infinity, what do you get? 0. Any number subtracted from itself is 0. Oh. Well, okay, this is indeterminate. In subtraction, you can't subtract two infinities from each other because you never know which infinity is bigger than the other, so you wouldn't know if you'd end up with a positive number, a negative number, or 0. So it is not able to be determined, therefore it is indeterminate. Okay? If you multiply, if you take infinity and you multiply it by a constant, this is your question about 2 infinity, double infinity, still just infinity, no matter what you multiply by. If you take infinity and you multiply it by itself, you still get infinity. But if you take infinity and you multiply it by 0, what do you get?
0.
No. Indeterminate. Why? Okay, well, because there's one rule that says anything multiplied by 0 is, there's another rule that says anything multiplied by infinity is infinity. We just said infinity multiplied by any constant is infinity. Well, isn't 0 a constant?
We could say no, right?
Yes, 0 is a constant. So there's two competing rules here. So it is not able to be determined.
Oh, infinity and 0. This is
Are infinity and 0 opposites? Yeah, they're inverses. Not opposites.
Yeah. Because the opposite would be negative.
Yes.
Yeah.
Yes. All right. How about infinity divided by a constant? How about infinity divided by itself? Oh, you guys can be very good. All right. The subtraction indeterminate form and the multiplied by 0 indeterminate form are concepts that you won't have to deal with again until you get to BC calculus or calculus 2 in college. But the division indeterminate form is something we will deal with in this class. So you don't have to worry about the other ones, but we will talk about infinity over infinity.
What about infinity divided by 0? Would that still be?
That is also indeterminate, yes.
So, K over infinity.
K over infinity, we're going to cover that one. Did I cover that one yet? K divided by infinity is 0, depending on the kind of infinity that you're dividing by.
Would it be like 0 plus?
All right, so we've got that rule we're talking about. Anything divided by itself is 1. And what are the two main exceptions? We saw one earlier. 0 over 0, and then the second exception is infinity over infinity. Okay, these are the indeterminate forms. These are the only ones we have to worry about in this class. Okay, to Micah's question.
There's more, I thought?
Well, yeah, there was the subtraction one,
Oh.
and there was multiplication one. Micah, this is kind of where you were going at. Okay. Can you divide k by 0? And the answer is no. We just did that in our notes. But could you divide k by 0 plus or 0 minus? Yes, that produces infinity. Can you divide k by infinity? Well, only if you know if it's a positive or a negative infinity. And if you get a positive, so this would produce positive or negative infinity, depending on 0 being positive or negative. Dividing by positive or negative infinity would produce 0, positive or negative. Those two are inverses of each other. Okay. All right, Aston. Did Mr. Taylor email us? Okay, I just haven't checked my email. Go ahead. Yeah.
For the homework, just a running question, do we need to write
Plus infinity or greater than infinity?
Okay, good question. The negative is required, the positive is implied. So I will understand. Like we don't write +2, I understand that you mean +2. All right, if you come across infinity over infinity in the indeterminate form, you should try division. If you came across 0 over 0, there were lots of things to try. If you came across 0 over 0, we tried FOIL, we tried factor, we tried common denominators, we tried reducing, we tried all kinds of things. If you come across infinity over infinity, there's only one thing to do, and it is division by x to the n, the highest n power present in the problem. So you want to divide by x to a power. And the power is going to be, you look at it, and the highest power of x you see in the problem, that's the x power you want to divide by. This is a legal algebraic move. So let me show you what I mean. If I plug in infinity right now, I will get infinity plus 1 over infinity. We learned that infinity plus anything is still infinity, which is indeterminate. So my algebraic strategy is to divide through by x to a power, whatever power is the highest present in the problem. What's the highest power of x present in this problem? 1. So I'm going to divide everything by x to the first. And by everything, I mean everything. So it's going to look like this. X gets divided by x. 1 gets divided by x. And the x in the denominator gets divided by x. That is dividing every term by the highest value of x to the n present in the problem. As long as you do everything. If you forget a piece, then now you've not done legal algebra. Then you're going to reduce and see what you have. Okay, what's x divided by x? Okay, is 1 divided by x reducible? No. And then x divided by x in the denominator is 1. Then retry plugging in infinity now. So now when we plug in infinity, we get 1 plus 1 over positive infinity over 1. And what did we learn is 1 divided by positive infinity? What kind of 0? Okay, so this would be 1 plus 0 plus over 1. We'll do the same thing for the denominator. You're going to divide everything through by the highest power, which should give you the exact same algebraic result. So I'll have 1 plus 1 over x over 1, the exact same as what I had, so you don't have to do it twice. Now plug in negative infinity. So 1 plus 1 over negative infinity, and dividing by negative infinity is 0 minus. So 1 plus 0 minus is going to give me 1 minus. So let me go back. This is a classic example of a horizontal asymptote because I plugged in infinity, and what did I get out? A constant. If you plug in infinity and you get a constant, this is a horizontal asymptote. All right, let's try another one. Oh, let's summarize what we get. Numerically, when we do it, we get indeterminate. Algebraically, we get a constant. So graphically, we get a horizontal asymptote. And it all works with algebraic division. All right, let's try another one. If I plug in infinity, I will get 1 minus 5 times infinity over infinity. 5 times infinity is infinity, so I get negative infinity over positive infinity, which is indeterminate. So I go back and say, all right, I'm going to divide everything through by the highest power of x present in this problem, which again, in this one, happens to be x to the first. So everything gets divided by x to the first. And then I simplify. And I will get 1 over x minus 5 over 1. And then I plug infinity into that. So I'll get 1 over infinity minus 5. I don't need to put over 1. Over 1's boring. That is 0 plus minus 5, which is negative 5 plus. So I plugged in infinity, and I got a constant. That means I have a horizontal asymptote, and I'm coming above the horizontal asymptote. It's on a plus, so I'm coming from above and landing on that horizontal asymptote. Yeah, Micah? Okay. The negative is going to be the same. It's going to produce negative, but it's going to produce the minus. So I'll be coming at the asymptote from below. Let's go on to, I want to try and get, how about this one? Let's skip the part, it turns out to be infinity over infinity. You can believe me on that. What will I divide this one by? I'll divide everything by x squared, because that was the highest power. So in my parentheses, I'll have 2x squared divided by x squared. I'll have 5x divided by x squared. I'll have 3 divided by x squared. I'll have 3x squared divided by x squared, and I'll have x divided by x squared. And then you simplify and see what in the world you end up with. I get 2. I get minus 5 over x. I get 3 over x squared. I get 3. And I get 1 over x. And then I can try plugging in infinity into that. If I plug infinity into that, this becomes 0 plus, this becomes 0 plus, and this becomes 0 plus when I plug infinity into all of those. So I will be left with 2 minus 0 plus 0 plus over 3 plus 0 plus. So 2 plus over 3 plus. Okay, any questions on that one? And we would do something similar for, actually it's going to be just 2 because the, shoot, I can't erase it anymore. The 0 plus is minus, yeah. Jack.
Are you dividing by 2 or x squared?
Because in the original problem, the highest power of that was present in the problem was a square. Whatever the high, if it was a cube, I would divide by a cube, the highest. Anywhere in the problem. Okay?
Sorry.
Okay, this is a famous function in calculus with properties that we're going to talk about today that'll be useful to you as you evaluate limits. It is the sine of a of x over the quantity x. The properties only exist in that form, so they don't apply if the a is in the wrong position. They don't apply if there's not an x in both the numerator and the denominator, so it has to be exactly this format. So what we want to look at first is something we've learned previously. We've learned last chapter, in chapter 0, the behavior of a hyperbola. Okay, a hyperbola is plus or minus 1 over x. What is the plus or minus control in a hyperbola?
The location.
The location of what?
The quadrant.
Okay, the branches. right? Controls the quadrant of the branches. In fact, go ahead and on your notes, you can call that a over x too. 1, it doesn't have to be 1, it could be 2, it could be any constant number that will create a parabola. But yeah, a positive parabola is going to give us branches that are in quadrants 1 and 3.
Positive.
A positive one, yeah, that'll be 1 and 3. That'll be a positive hyperbola. And then the negative hyperbola has branches in quadrants 2 and 4. The sine of a of x over x is a graph that is bounded in between those branches. It will never go outside of any of those values of the branch. So it oscillates very small as the branches are squeezed together, and then it will widen at around the middle, the symmetry. This has even symmetry, and then it will kind of compress again as the branches squeeze together. This is the graph of sine of x over x. However, something important happens at this peak part, which I couldn't get my computer drawing to do, but you'll have to add, is that there is an open circle right there. There is a limit approaching from the left, and there's a limit approaching from the right, and they are approaching each other, but they will never actually reach that point. It's not closed. It is an open circle, and the position there is at the value of a. Whatever the a value is in the equation of sine of a of x over x is the same as the value that it will be approaching. It will never exist there, but it will have a limit. So we say the following is true. We say that the limit as x approaches a of this function f of x is a. Sorry, not approaching a, as approaching 0. My fault. As I approach 0 from the left and I approach 0 from the right, the function waves of this graph will approach the value a at like amplitude. But f of a, oh, I keep doing that, f of 0 does not exist. Okay, so the limit exists, but the function value does not exist because of the hole that's there. So that's an important property for you to understand. Okay, go to the next one. We're going to talk about the left, right, and middle behavior here. Hi.
All right, I was doing.
Okay, as x approaches negative infinity, that means as I'm heading out here, the branches are compressing that graph. Okay, so the oscillation just gets tinier and tinier. And so it's approaching that the x-axis as an asymptote. And so we say that the limit is 0 because it's getting squeezed so much down. Will it ever actually approach 0? Or get equal to like be 0? No. Does it cross 0? It crosses 0 a whole bunch of times. Cross 0, cross 0. Every time it oscillates, it crosses 0, but it'll never just totally settle on 0 and be 0 forever. It's going to approach that value. Same thing on the right. That also we say has a limit of 0 because it's compressing its oscillation. It's crossing the x-axis a bunch of times, but it'll never actually ever be totally 0 forever. And then in the middle, we've already talked about that on the previous slide, that the middle has a limit value of a, which is the peak it would be at, but it will never actually get there. So these limits never actually get to the limit, but they approach the limit. So these can make some multiple choice problems really easy. You should be able to look at a question like the limit of the sine of 3x over x. And you should be able to go, oh, I know what that limit will approach. Okay? The limit will approach 3, and it's one and done. Like it's really that easy if the equation starts out like that. The a value, if the sign is there, Okay, it doesn't work for cosine. So I'm just telling you, it has to be sine. It has to be in the form ax, and then you have to have x approach in the denominator. All of that has to be true. Okay, so try here. What if it's like this? What if we're trying to do the limit as x approaches 0 of the sine of 2x over the sine of 3x? Does it have all the pieces that you need? No. What's it missing? Okay, it needs the x in the denominator in order for this to work. All right, so is there something now you're going to have to do some algebra? So we say equals, put our equal sign in the front. Then limit comes next. And then sine of 2x over 1 multiplied by 1 over the sine of 3x. I'm hoping that you agree with me that that was legal algebra to do. I can divide something by 1, and I can multiply it and have it, it's all still the same. It is all still equivalent. Okay, so that's a legal move for me to do. It's also legal for me to multiply this one by x as long as I do what else? Multiply the other one by x. That's legal in algebra to do. So now I have created this in the form that I need. I have now sine of 2 of x over x, which matches this format I needed it to be in. And so now I've got, all right, well, that first one is going to have a limit value of 2. Let me do it like this. And the other one, it holds true even if it's upside down.
It's separate. Can we do limit simple, or does it have to be just? Oh, I know you're multiplying.
I'm multiplying, yeah, this is a multiplication. Into separate denominators?
No. You can have the limit going into 2 different sections.
Mm-hmm. Yeah, that was one thing it was in the properties of what you are allowed to do. You are allowed to multiply limits as property number 3, that you can multiply 2 limits together. Okay. All right, so let's back that up. Where are we at here? Okay, and so this will just be 2 times 3. There we go. So the answer to that would have a limit. Oops, so sorry. I gotta get this right. 1 over 3, now we have it right, so we get 2 thirds. Okay, if it's upside down, then the a value is upside down.
Where'd you get the 1/3?
It's this limit here, but because it's in upside down format, it's not 3, it's the reciprocal. It's the reciprocal of this one. So then the answer is not a, the answer is 1 over a. You want me to write that out for you? Sure. We'll add a second one here that says, so you're okay if I put the limit here that you get that that's equal to a.
Yeah.
Okay, so then we could add underneath it that the property is if it's x over sine of a, if it's upside down, then the limit is 1 over a instead. Okay, yeah.
So that means from both the left and right, it'll be approaching 2/3.
Right.
But it'll.
Yep, it'll be approaching 2 thirds, but never actually get there. So the whole would be at 2 thirds. Above 0. 0, 2 thirds is where the whole would be. Okay, let's try another one. What about this? What's wrong about it? Okay, it should be, it's tangent and it's not sine over cosine. So what could I do about that? All right, well, let's look at the algebra of what we can do. So we saw before we can take tangent of 4x and put that over 1 and then multiply this by 1 over x. That's the same thing. We're just separating this out. Division is the same as multiplying by the reciprocal. This is the same algebra. Then what can I change tangent into? Sure, I can change tangent into sine over cosine. So the tangent of 4x would become the sine of 4x over the cosine of 4x, still times 1 over x. So that's legal. Okay, what's still my problem though? So now I have the sine that I need, but what else do I need? I need x to be where? In the under the sine. I need the format to be sine of a over x over, and I need x to be under that one. Right now, x is under the number 1. I need x to be under the other one. This is multiplication. Doesn't matter in multiplication the order that you do things. 2 times 3 and 3 times 2 are the same. It works in the numerator and the denominator, so I can flip-flop these. And I could put x under that one. And then I can put the cosine under this. All right, that's legal. Now this one is correct in the correct format. So what does the limit of the thing in the red circle turn out to be? 4. Okay, and then what can I do with the number 4? I can pull it to the front because it's now a constant. That's one of the properties of limits, is that you can pull the number 4 out to the front. So now this becomes 4 in front of the limit of 1 over cosine of 4x. Now what do I do? There is no property for cosine. Okay, there's only a property for sine. There is no property for cosine. So then you just go back to the very first thing we ever learned about limits, the very first strategy we learned about limits, and you always try and just plug in the number. Can I just plug in the number and see what happens? Well, let's plug 0 in and see what happens. So now I don't need limit anymore because I'm replacing 0 with a number, or x with a number. So it's 1 over the cosine. And if I plug in 0, I'm going to have 0. Well, what is the cosine of 0? Cosine of 0 is 1. It's 1 on the unit circle. It's 1 on the cosine wave. So this is 4 times 1 over 1, which has a limit value of 4. All right, let's try another one. All right, what would we, yeah, Andrew.
So, if we know it's like that, basically, can we just skip all those steps? Because we know it's tan 4x is going to be over x, so you can just take off 4 and just know it's 4.
There's always one person who asks that, and I'm glad it's you. Okay, so my answer is, it depends on what kind of question it is. If this is a multiple choice question, and you're like, tangent of 4 over x, tangent of 4x over x turned out to be 4. I wonder what the limit of tangent of 5x over x would be. It's going to be 5. I know that's okay. If it's multiple choice, pick it. Okay, but if it's a free response and it says justify your answer, okay, and there's 5 points associated that I'm looking for the algebraic proof of how the steps go. Okay?
So I'm like,
yep.
It feels more complicated than this.
Yeah, so I'm showing you a proof of why it is.
Okay,
yeah.
that works.
The last one was like sine 2x over sine 3x, and then we got 2/3.
Uh-huh.
So is that like all of them are going to be like that?
Yeah. So if it was 5 and a 7, it would be 5/7. Okay. Again, if it's multiple choice, go right ahead and pick it. But if you're asked to prove it, you should be able to prove it. Yeah, Micah.
Why did we lose the 1 over x?
Where did we lose? We did not lose the 1 over x. It traded places with the cosine of 4 over x. Look at the order of your numerator and denominator. Here, I'll show you. A over b times c over d. You can flip-flop a over d and c over b. You can change the order of those, and that would be totally fine. So what we did here is we switched the order. The cosine came first and the x came second, and the next step we had switched their positions, which is legal. You can only do that in multiplication, right? Like you can't do that in adding or subtracting of fractions. Like don't think that you could go a over b plus c over d. Oh, I can just flip-flop and put the d first and then put that's totally illegal. It can only work in multiplication because multiplication is what's called commutative. But adding of fractions is not. Okay. You probably have a gut reaction of what that one's going to be. You might. You might. Okay, Andrew thinks it's going to be 1/3. Can you prove it? He's right. The answer is 1/3. So if it's a multiple choice question, great. You get to say it's 1/3. But can you prove it's 1/3 with legal means? Oh, you know what? You're wrong. It's not 1/3.
Oh crap. Oh wait, because it's going to.
It's going to infinity.
So it'd be 0 is more.
It's going to be 0. Can you prove it? Can you prove it? Okay, so separate again. The sign of x. What would we like the denominator to be? X. What's extra?
1/3.
Okay, the extra is they're separate. Okay, 1/3 is a constant. And so what can you do with every constant? Pull it to the front. So this is going to come out in the front of my limit. So I'll have 1/3 in the front of the limit. And sine of x over x when x approaches infinity is 0. So 1/3 times 0 is 0. You have to watch what x is approaching. It's only a if x is approaching 0, because you're in the middle of the symmetry of your graph. If x is approaching infinity, you're on the edges of your graph. That's why. Okay, how about this? Yeah. Thanks for catching me. All right. You might have a gut about this one too, but you got to prove it. Yeah.
Sorry, for the previous one, it's when we plug in infinity, it would be sine.
No, we don't plug in infinity. There's no plugging in infinity.
No.
It's a property.
Yeah.
It's a property so it's a property that we have now. Okay, we'll be able to prove it. You have to. I'm telling you that that's the value right now. I know you want proof. You just don't quite know enough math for me to prove it to you, but I can prove it to you in about 3 weeks. Okay. All right, you might have a gut about what this is going to do, but we want to be able to prove what this is. So this is an addition problem. We haven't seen an addition problem yet. We've only seen multiplication. So we got to know what's legal for us to do in addition. Now clearly we want the x to be under the sign. And so we're going to set this up 5x and sine of x. And we want to put the x under the sign. What do we put under the 5x, Luke? Also x. Okay, don't 1. That would be multiplication. This needs to be, they both get an x because this is adding, and adding is common denominators. The 5x over x can reduce. So I'm going to have the limit as x approaches infinity. That will reduce to plain 5 plus the sine of x over x. Right, can I pull that out in front? I can, as long as I have a 5 plus then, not a 5 times. So this would be 5 plus the limit of x approaching infinity of the sine of x over x. So now that limit that's left, Jackson's just going to have to trust me that it is 0. So as much as I'm able to show you right now, I'm trying to help convince you of it by graph. I'm trying to convince you of it that sine of x over x gets squeezed, and so it has a value of 0. I will be able to give you a rock-solid proof, but it'll have to be in September. So this will be 5 plus 0 equals 5.
Like, what is it? Is it like derivatives or something?
Yeah, it definitely involves derivatives. Yeah.
Like, what's it called?
L'Hopital's rule.
Yeah, I don't know what that means.
Yeah. He's a French guy, Guillaume L'Hopital. He was a French mathematician, so it's named after him. Yeah.
So does it mean that this graph was shifted 5 up?
This graph is shifted 5 up.